Hi, everyone. Good afternoon or good morning for some other folks out in the West. Hope everybody is doing great. I just need a confirmation from my colleagues that everybody can see my screen before we can get started.
Yeah, I can see. This is Lisa.
Okay, perfect. Thanks, Lisa. Thanks to everyone for making the time to jump in this presentation. We have a nice amount of people attending right now for the Abaqus 2020 product update. So it's kind of like a tradition that we do here in the company. So with every release level, we make sure that we present the latest updates and the latest features and upgrades to the Abaqus. So just a quick overview of our presentation about us. I know most of the attendees are our clients, but we have some other attendees. So I'm just going to go over a quick presentation of the company, then a presentation about myself, and then we're going to head to the presentation of the Abaqus 2020 features update. So as Aventec, we are Dassault Systems Gold Partner, a proud team of PhDs and masters with expertise in multiple industries, but mainly oil and gas, aerospace, automotive, industrial equipment, and marine and offshore. We offer services in the 5 main brands of Dassault Systems: Simolia, Katia, Delmia, Innovia, and Excelli. And we also offer solutions in 2 complementary softwares, TrueLoad and Meshworks. So basically, our objective is to identify the discrete and underutilized and insufficient processes in order to help companies, mainly our customers, to evolve the silo culture to transition over the processes that encourage clarity, visibility, traceability, and high organizational efficiency. I'm just gonna take 30 seconds to present myself today. I'm gonna be your speaker. Hisham, I have a PhD of mechanical engineering. My field of research was in stealth fracture mechanics. I joined Aventec a couple of years ago, well, exactly 2 years ago. Prior to that, I worked for about 8 years in the R&D as engineer scientist, among other roles. And my main fields of research right now are material modeling, fracture mechanics, composites and polymers, and fatigue. Sometimes I do also fatigue creep interaction, which is a hot topic for several industries right now. In today's presentation, I'm going to be talking about mainly 6 different parts. I'm going to start with the most exciting part, which is Abaqus CAE enhancements. Then on features, then I'm going to go to talk about contact constraints, linear analysis, nonlinear mechanics, Abaqus explicit, and then we're going to talk a little bit about the solver, and then we're going to wrap up. I'm going to try my best to keep the time about 55 minutes for the presentation, or 50 minutes, and then feel free to ask any questions, drop them on the question box, and then I'll take my time to answer them at the end, or I can always email you back towards the end of the day with any other answers. So again, thank you everybody for taking the time to attend today. So our first stop will be to talk about the Abaqus CAE 2020 enhancements. Before I just have to show this legal notice. So mainly to summarize it, it's basically, please do not make any purchase or any engineering decisions based on the content of this presentation, just a matter of liability, and I appreciate your understanding. So Abaqus CAE 2020, what's new? One of the very exciting I would say, like, one of the very exciting upgrades to the Abaqus is the direct import of SolidWorks files. So now we don't have to switch or convert files from SolidWorks to STEP or IGES files and then re-import them back, especially for large assemblies. It might be complicated. So now we can import directly parts as a solid part or solid assembly directly from the CAE. Previously, in terms of also the partition, we couldn't partition a 3D model or 2D model if the edges were not if the edges were free. So now we can do that, and that was like a painful limitation, personally speaking. Renumber the nodes and elements from an assembly context, it's a nice upgrade as well. So now we could pick an orphan node or element from an orphan mesh, or even from a part instance, and then we can start the renumbering according to a certain sequence. This feature is very important especially for the folks that deal with a lot with pipe elements and elbow elements, especially with the inclusion of the PSI elements, because the numbering is quite critical. So this is a very nice feature to consider. Query using the local coordinate system. Prior to this release, we could only query in the global coordinate system, but now we could switch to the local coordinate system. And we could query based on point, node, distance, geometry face normals, or element face normals as well. For the folks that like to use Python within Abaqus, or a lot of us, we have our own scripts. So there was an upgrade to the Python version from the 2.7.9 to the 2.7.15. Again, not to the 3.4 as some of our clients was anticipated. There's also the inclusion of the SciPy, SymPy, and Matplot libraries are now included with the Abaqus Python, and they're accessible through a command window. Contact initialization for Abaqus explicit could be picked from the CE window. Based on the creation of the contact initialization, the user can pick directly if the contact initialization is Abaqus standard base or Abaqus explicit. And now the start TENSILE failure material model is supported from CE. In the past was always a pain to just like include it in the IMP file. This model is used in conjunction with the Johnson-Cook plasticity model, mainly in Abaqus explicit. And it's basically a sub-option for plasticity models or for equation of states for the folks that deal with smooth particle hydrodynamics, for example. The evaluation of Hyperfoam material test data in the past were that feature has been there for a while, where we could evaluate material test data from viscoelastic and hyperelastic material models. Now we included the Hyperfoam material models as well. The color code, which has been introduced in the latest, if I'm not mistaken, the latest maintenance release of 2019, which is like hotfix 3 or hotfix 4, pardon. So this partition or color code by geometry face can make like the visualization more easier, especially for complex geometries or even for complex assemblies. And the color code and the attribute managers, for example, for the load manager, we can see that there's been the introduction of the color coding based on like red, green, and yellow, modified, deactivated, and active. This feature has been introduced in the Abaqus 2019 hotfix 3, so it's been available since last year's release, and it's been upgraded there. So that's basically the main features of Abaqus CE. Now we're gonna switch gears and talk about the contact and constraints a little bit. So one of the main issues was to deal with the interference fit, especially for Abaqus explicit. We know that the Abaqus explicit solver handles the contact problems with more robustness compared to standards for most part. But when it comes to overclosure, sometimes we have a lot of issues, and it's been a little bit tricky to solve the interference fit when it comes to problems with dynamic problems that are easier to solve with Abaqus explicit compared to Abaqus standard. So this sorry, just so this I would say like this capability has been introduced right now to Abaqus explicit, and sorry, yeah. So just we did like a quick benchmark here to benchmark the results of where the same models being solved using Abaqus explicit and Abaqus standard, and we can see like the nice distribution and the nice distribution of stresses around the specific areas, of course, except areas where we have like high local stress concentrations because of the nature how of the solvers and how organically they handle the stress concentrations locally. Sorry. Initialization control for general contact. Previously we used to use the keyword star contact initialization data and contact initialization assignments. These keywords were only applicable to Abaqus standard, and now they are available in Abaqus explicit as well. And these options includes also the contact clearance assignments. The basic keyword specifications to treat initial overclosures, for example, for interference fit are initialization, inclusion, exclusions, assignments, etc. So these keywords are also now available within the Abaqus explicit. So just carry on with the contact initialization controls for general contact. So now we can specify the interference fit distance that differs from the initial configuration, depending on percentage of the initial overclosure. So we can include certain keywords to specify the distance. Again, these availabilities have been available for a while in the Abaqus standard, and they are being included in Abaqus explicit just in this current release. The contact status legend, which is basically a nice, I would say like a nice way to know the contact status after for an analysis. It's being included or upgraded in Abaqus standard and explicit. For the old Abaqus status, for the old contact status was only kind of like 3 options, so closed or open. Now we added the sticking and slipping status to the legend. The thermal expansion of a rigid light features. I know it might sound a little bit tricky, but sometimes we deal with we use like rigid bodies to make our analysis quite lighter. And at the same time, we need certain information when it comes to thermal analysis, especially the thermal expansion, if you want to include it. So now we could include the this feature in the rigid bodies, kinematic coupling, beam multipoint constraints, and link multipoint constraints, which is a very nice and useful, and it's comparable to or similar to the NASTRA and RBE2 capability. So I'm just going to show like a quick, illustration here for the 3 equivalent models, such that the inner sleeve of the nodes is constrained follow the motion of the center reference node. So like there are like 3 different ways to do it, either using a kinematic coupling or beam MPC or a nodal set of rigid body. And these 3 different scenarios, we can still include the expansion coefficient as part of the simulation. Material-based property assignments for general contact. I remember last couple of years ago, 2018, and then upgraded in 2019, we talked about the friction coefficient material-based assignments. That was a nice upgrade for the general contact capability within Abaqus standard, and then also within Abaqus explicit. Now we can also include the material-based property assignments instead of only section-based or part-based assignment. So from a general contact perspective, it would make life quite easier, especially for large assemblies. Small sliding formulation within general contact has been also included. So of course, when we deal with general contact, we also have to keep in mind the way that the slave surface is moving accordingly or opposing to the master surface. So basically, we're talking about, or we can distinguish between small sliding and finite sliding according to the convexity or if the surface is plan. So this consideration has been also included in general contact within Abaqus standard. And then, of course, there's a directional preference in the user subroutine friction coefficient that can treat the anisotropy friction in Abaqus standard exclusively. And then we can also specify two different friction coefficients based on, I would say, like transverse anisotropy within the same user subroutine. Linear analysis, there is a nice emphasis or a nice concentration on the effort when it comes to large models, where we don't have to use multiple steps models, but instead using just like one singular step in a linear analysis, but with many load cases. So many efforts have been put towards removing the limitations due to the number of load cases for large models, and then improve the performance of writing the solution into the internal Abaqus database, among other improvements. And these efforts have been going on for a while, since Abaqus 2017 up to 2019 at the latest release, and then of course has been also improved in the current release. When it comes to linear dynamic, I could note like a bunch of improvements. Some of them are quite deeply related to the solver technology that we're going to be talking in a separate section later during this presentation. So we can talk about the large-scale eigenvalue extraction analysis, enhancement related to the residual mode functionalities that's been introduced in Abaqus 2019, the hybrid CPU-GPU frequency response solver, and the improved result output performance in the model analysis procedure, among other capabilities. For non-linear mechanics, we're going to touch base about like 3 different sections, and we're going to start with element technology first. So there's introduction of the new pyramid heat transfer elements. So back in 2018, we introduced the structural pyramid elements, where they help a lot with the transition between brick elements or hex elements to tetra. And it was a very nice capability. Unfortunately, the capability is not yet available through CAE. So basically, there's a bunch of keywords that we have to consider in our mesh, in our input file. So now this capability has been expanded to the heat transfer elements, and basically considering the same philosophy of making the transition between brick elements or hex elements to tetra elements quite smooth and easy. Improvement to fluid pipe elements. So now we can define the non-Newtonian viscosity behavior for the fluid flowing in pipes. We can define the Newtonian viscosity, power law, Bingham plastic, and Herkel-Buckley. When it comes to the material enhancements, most of the focus have been more oriented towards creep and yield material models. The first enhancement I'll be talking about is basically enhancement related to the VUMAT or the material user subroutine in the Abaqus explicit, where we can include the effective Buck modulus and the shear modulus into the user subroutine. This modulus is basically used in Abaqus explicit, as I said earlier, and then it could be included directly through the CEE, but within the user subroutine. There's the introduction of the new yield surface of Chaboche, the rate-dependent yield. So the keyword from the user of the user's interface is basically star plastic with hardening equals combined, and then we can include the cyclic hardening in the array dependent, and then new type equals Chaboche that will include the array dependency of the Chaboche law. This law could be used conjunctly with nonlinear kinematic hardening, Mises, Hills, FEFB, PRF, Drucker-Prager, and crushable foam plasticity model. There are also some enhancements related to the creep models that actually are the existing creep models already used in Abaqus. So we run into so many problems related to the, I would say, like the parameters used in these models. Some parameters have non-physical, I would say, like non-physical sense, and also non-physical units, which make the conversion a little bit tricky. And also, like some parameters, they would tend to be very small, which caused very high amount of numerical convergence issues related to these parameters. So what we did is basically rewrite some of these material models. I'm just going to give an example here of some. So the current creep law, for example, the time strain Bergstrom Boise. So there's the current form and then the new form, and then the conversion. So these two forms, the current form and the new form, are exactly equivalent. It's just a matter of make the conversions more smoother, and but the physics behind is basically the same. There's also the introduction of the non-quadratic yield surface for plasticity, especially for within Abaqus explicit. This capability has been introduced in the latest, the last maintenance release of Abaqus 2019, and it's being carried on to Abaqus 2020. Mainly, there's the introduction of the plasticity with anisotropic non-quadratic yield surface, Barlett yield criteria, and then plasticity with isotropic non-quadratic yield surface, noted as Horsford yield criteria, and also Tresca. So there's also the introduction of the improvement of the capabilities with behind the keyword star potential. In the earlier releases, the keyword was only used to define the stress ratio for the Hill's stress potential function. Now we can define the coefficients for various stress potential functions, such as Barlett, Hill, Horsford, Tresca, isotropic yield, etc., within Abaqus explicit, of course. There's also an emphasis on introduction of the memory alloy, or known as superelastic materials. So there's kind of like a switch into the default of the modified formulation used in this in order to model the superelastic materials. So the environment variable for switching two formulations in either in standard or explicit have been changed. There is also the modified formulation that it's been introduced back in 2018 and the latest and the last maintenance release. And now this capability is also available through CAE. There's a new subroutine utility routine, which is labeled or named under GETPHYSICALCONSTANTs, which help to call by any, which can be called by any other user subroutine in order to obtain the values of the defined star physical constants. We can name some variables such as absolute zero, the Stefan Boltzmann constant, the universal gas constants, etc. In terms of the prescribed assembly loads pretension section, I'm going to be talking a little bit about the bolt load, or the bolt pretension torque. Some of us are quite familiar with it when it comes to large assemblies that we use bolt tightening torque in order to apply what it's called a pretension. This technology actually has been patented by HKS days before the Samoya brand, and the assumption that is being based upon that the tightening torque is basically unidirectional, and like the normal stays always normal to the pretension section facets, which is not very true when it comes to large rotations or large displacements, for instance. So, for example, like this lap joint here, when we apply a pretension, then we apply like a large deformation, the direction of the pretension's force will definitely vary according to the rotation in the space. So the enhancement is more related to this specific capability, which now we can introduce if the force is a follower force or no. So the keyword is basically start pretension section, and then we can add follower equals yes or no if we want to include large deformations or large displacements and large rotations. It's just like a quick animation of the same lap joint with and without. So basically, the Abaqus 2019 results versus the Abaqus 2019X, which is the latest release where we introduced this capability. And we can see that how the volume stresses distribution versus the angle of rotation stayed quite smooth as opposed to the older assumption. Another hot topic that I'm more excited to talk about today is fracture mechanics. We focus the development of the different fracture mechanics capabilities, I would say, more towards fatigue crack growth, especially for low cycle fatigue with high amplitudes, coupled thermal displacement cohesive elements and thermal pore pressure displacement elements. So let's talk a little bit about the fatigue crack growth analysis. So last year for Abaqus 2019, we introduced a specific procedure under STAR fatigue, which is basically or specifically works as part of to model the cyclic loading, mainly high cycle fatigue, which supports mixed mode fatigue loading, among other stuff. So there was a tremendous effort was put towards enhancing this capability, mainly improving the accuracy under the mixed mode loading, obtain the mesh independent smooth crack front, which is basically part of the effort put towards developing the XFEM technology. I remember last year we talked about the introduction for the first time of the crack branching, so this capability is being pushed more forward. We can talk about also the alternative methods of smoothing the crack front based on the damage state of the bonded node. Property account for damage element debonded length when the all adjacent node are debonded, and also the account of mode dependent stiffness degradation. A couple thermal displacement cohesive elements have been also introduced, which is a very nice capability. It makes life easier when we deal with the complex or multi-physics simulations, which include cohesive elements. Coupled thermal pore pressure displacement cohesive elements are also being introduced. So these libraries are unfortunately only accessible through input file. Again, there's a huge push forward to make these libraries available through CAE as well. In terms of Abaqus explicit, we're going to talk about the element robustness improvements, specifically oriented towards the distortion of displacement thermal base element deletion, which is backed out with the fracture mechanics efforts, linear kinematic conversions for continuum elements, and as well as the improvement of the C3D8 incompatible kinematics. So when it comes to the distortion of the displacement thermal base element deletion for material undergoing basically extremely large deformations, the element may become distorted, or as we call it, with negative volume, which may occur more on a numerical, I would say like a numerical aspect, even before the material reaches yielding point. So the element deletion is basically intended for to just remove these elements from the simulation in order to push the conversions forward. Basically, we have to be careful because it's more intended for experienced user and should be used with very cautious, because setting up the improper values can also lead to a non-physical or even misleading results. For deletion measures, we can talk about the element stable time increment when it comes to Abaqus explicit, the volume area, and the characteristic length, because these are the main, I would say like the main parameters upon which the solvers base the stable time increment for dynamic or even for quasi-static analyses. We have to compare the measure to a specific or specified threshold, and to compare the ratio of measures to the original measure to specify the threshold. The keyword used is section controls, delete distortion elements. Yes. Just this not to be confused with the element deletion when we deal with the damaged elements. So this is basically, this technology is more used to help with conversions rather than solving a damage related problem. So that's a little bit to avoid the confusion. And then the linear kinematic conversion, when the element becomes highly distorted, there are currently like two options. So trigger the fader error and end the simulation, which is basically that's what the solver is going to do, or we can delete the elements. The new option is basically to convert the element to behave linearly. It's going to compromise a little bit the analysis if we're dealing with high amount of nonlinearities, but it's going to help at least to get our an idea or a sense where the simulation is going. This technique is basically applied to the current elements right here. So C 3D4, 3D6, 3D8 reduced integration, the hybrid and the modified version of those elements as well. And the keyword is basically section, because section control, name of the section, distortion control, yes or no. And we can define the length ratio, which is, we have to specify a ratio value. The default value is 20%, and the length ratio could not be more than 80%. Otherwise, we're going to trigger like certain conversions issues. I can talk also about the improved of the C3D8 incompatible kinematics, which is additional incompatible modes that already were implemented in Abaqus explicit to make the formulation consistent with the Abaqus standard. We did remove the bilinear pattern in the hydrostatic stress for approximately incompressible material. Because basically whenever we deal with highly incompressible material, quasi-incompressible materials, we always tend to use hybrid elements. In some cases, scenarios is not the more ideal, I would say, solution. So now the incompatible material, the incompatible mode elements can help with the conversions in terms of solving this class of material. So this is just like a simple example where comparing Abaqus standard formulation using the incompatible mode elements within Abaqus standard to Abaqus explicit, and then the issue that is being solved with the additional incompatible modes that have been incorporated into the new elements, and we can see like the conversions compare between the two models. In terms of the contact linkage for the coupled Eulerian Lagrangian capability, which is basically one of my favorites when it comes to very large deformations and large distortions, we used to have some issues when it comes to rapid dynamic simulations, for example, like ballistic explosions. the problem is being labeled under like gas leakage, which basically can occur under high pressure gradients and flow rates tangential to structures, sharp corners area when it comes to dealing with sharp corners in a structural mesh, large motion of structural mesh through the Eulerian domain, etc., or a combination of all of the above. So part of the enhanced CL coupled the Eulerian Lagrangian contact formulation, there was tremendous effort towards improving this, I would say like this bug-related issues that now can be used with both solid and shell elements. The structure should be thick enough to avoid multiple surface intersection at the same Eulerian domain. The leakage may still occur where a single CEL element is intersected by multiple surfaces, something we call label as the T intersections. The shell surfaces must have different materials on opposing sides. The enhanced formulation is more expensive than the default formulation in both CPU time and memory usage as well. The keyword is star adaptive mesh refinement, element set name, and enhanced contact. Yes, it's basically as simple as that. The default is enhanced contact equals no, so just basically switch the no. The enhanced CL contact formulation works best for continuum meshed Lagrangian bodies. Inside of Lagrangian body must be initialized with the void material, and it must also be large enough to that a single Eulerian element does not get intersected by different surfaces, as I mentioned in the past slide. Lagrangian bodies mesh with shells can also work if shells are thick enough so that the single CEL elements cannot span their thickness, and shells meshes must have consistent element normals. We have to be careful when we deal with like shell when we switch curvatures, or we have like cylindrical shaped shells. We have to be careful when we deal with the element normals. Positive surface normals must be point in directions of approaching material surface. Couple of specific or special considerations exclude the symmetry surface from the contact. If two surfaces intersect the same CL element, the old method is used basically, which may trigger some leakage, and shell structures cannot be embedded in a single fluid. A nice example here to illustrate the CL new improvement is a blast benchmark problem. So we have a bunch of Lagrangian bodies, basically aluminum, steel support, steel boxes, and weights on top of the steel box, which is basically were modeled using discrete elements. And then we have the Eulerian domain, which consists of soil, air, and C4 explosive buck. We just considered quarter symmetry and 0.005 second event, and we use general contact for this. So just like a quick glance of the type of elements that we use in the Eulerian domain, Lagrangian domain. Three material are being highlighted here, along with the rigid body. So here we're going to see the difference between the new algorithm and the old algorithm. We can see like also the difference here in terms of the leakage that it's happening at the steel plate level. And keep going further into the step, we could see like the amount of leakage that we're having like through the steel elements compared to the volume fraction. It's very considerable. And towards the end of the simulation, we can see like how the kind of like, I don't know if I call it leakage or like just the whole physics is being screwed up here because of that convergence problem related to the leakage issue. In terms of Abaqus explicit enhancements, we introduced the new hybrid MPI or message passing interface that it's now available in Abaqus explicit. We introduced this a couple of years ago in Abaqus standard. Back in the days where it was like hot technology. I know a lot of us, we don't really deal with that kind of very high fidelity, very extremely large problems, but some of our customers have been dealing with 5+ million degrees of freedom, and this hybrid technology have been making their life quite easier for Abaqus standard, and now it's being incorporated in Abaqus explicit. So it could be used just simply from a command line hybrid parallel running using 2 MPI processes per node seems the most optimal case. There are no restrictions on the MPI types. Could use from Intel or from IBM, or both works with no restrictions for high performance computing. The performance is basically optimal on the core counts between 40 to 200. But again, it's very problem dependent. Sometimes we might find that paralyzing problem might make things more complicated. Sometimes might make them easier. So it's a very problem-related approach, I would say. We'll work also on a single node and single process using multiple threads. So this is just a very simple drop test comparison between the DMP and the distributed message passing interface, old technology, and then the DMP with enhanced technology, and then of course with the hybrid technology. So we could see like the improvement 16, 18, and 10%. Capacity improvements in terms of the explicit packager have been also incorporated. I know I did not want to include so many examples here, just not for time purposes, in order to make this presentation as light as possible. But now we could do like a crash analysis of 8 cars in a parking lot without an issue in a very reliable manner. Parallel scaling enhancements have been also introduced in order to reduce some issues caused by the node share with many domains, and specifically it's a common issue when it comes to large rigid bodies. Optimize rigid body contact communication that would make sometimes it makes the most of the time it makes the models quite lighter, quite efficient in terms of run. But the issue is basically when it comes to contact between several rigid bodies. So these capabilities have been also introduced in order to improve this capabilities. The B multi-point constraint spiders are now handled more efficiently in general contact. And now we're going to talk a little bit about the solver technology before we wrap up. Basically, we're going to talk a little bit about the constraint preconditioned iterative solver. A couple of you back in Abaqus 2018, we introduced the iterative solver, and it was I remember back then in my presentation I did like a huge section on the comparing the iterative versus the direct solver and the efficiency of the iterative solver versus the direct solver. There's a drawback when it comes to small size models. A small size means like the number of degrees of freedom. So under a million degree of freedom, we don't really see that much power as opposed to 10 or 15 million degrees of freedom. So now the constraint preconditioned iterative solver can support so many I would say procedures, general procedures. So basically, we can just incorporate the solver equals iterative at the step level, and then do like a star static. We can do the same thing for quasi-static analysis and also for implicit dynamic. There are some few limitations that I would like to just highlight here. The iterative solver generally cannot solve a problem reliably if the direct solver issue the following message. So if we have like a negative eigenvalue or zero pivot, that's more related to the problem definition of this, or the model definition, how it is, and it's more like boundary conditions and the whole setup of the model. Numerical problems or singularity warnings, again, that's my pop-up, but it's more related to the problem definition and not to the solver incapability of solving the whole model. The iterative solver cannot solve the problem if the model is over constrained, may experience convergence problems due to the precondition or setup failure. And of course, asymmetric matrix is not fully supported. We can deal with this in term when we are dealing with high nonlinear contact issues, where we engage the unsymmetric matrix that can definitely help with some class of problems. So keep in mind that the iterative solver cannot be engaged in those case scenarios. And for the geostatic procedure and coupled pore fluid diffusion and stress, star soil procedure analysis are not supported yet for model with Lagrange multiplier. Running the iterative solver incorporate a little bit of tricks and modification to the environment variable in the Abaqus _v6 environment file. I would say really consult with myself or with one of my experienced colleagues before you go ahead and play around with the environment file, because it's very crucial. And if there is any error or anything that messed up there, it can definitely affect the whole solver stability and the whole installation of Abaqus itself on the machine or on the server or whatever you're using it. So yeah, the command for proper HPC host configuration, I just put like a line, which is like, I know it might sound crazy that I engage like 120 core, which is just crazy, but just to showcase of how the line could be just included. And just to touch base quickly on the performance of the iterative solver. So just an example that I put here that incorporated part train model with the hard contact. The number of elements are about like 4 million. The number of nodes is about like 6.3 million. And number of degrees of freedom is about 18 million degrees of freedom. And the number of flops is too much. It's about like 280 billion flops. So we went through different configurations, mainly a comparison between, again, like the direct solver and the iterative solver. And we just introduced the performance index of the direct versus iterative. So including the host configuration, the number of increments, the number of solving passes, the average iterative solver pass, and then the standard wall clock time in hours. We can see like how the iterative solver is by far better. It's much faster in terms of solving this class of problems with more efficiency. And we can tell from the results that basically we're talking about the exact same. The convergence ratios were exactly the same values and everything, except we're getting better convergence in terms of time with more efficiency. Here again, as I mentioned at the beginning of the last section, the drawback is basically related to the size of problems. If we're dealing with very large problem, engaging the iterative solver might even slow down the convergence as opposed to make the convergence faster. And again, it's very problem dependent. So we can go from small number of degrees of freedom, about 1 million. We can see like the scalability that can go more up and up as we are converging towards more larger models, and we can have like a speed up factor about like 6 to 7 sometimes. As per the memory usage, again, the same thing or the same conclusion can be drawn. The memory usage factor compared to the between the direct and the iterative solver. The more we engage the iterative solver, the more we suck more memory, unfortunately. But it's more optimized in terms of the memory usage and the memory solution as well. The speed up factor compare between the two solvers here. Again, as more we converge towards large and large degrees of freedom with a large amount of flops, we consume more memory. But the drawback, the advantage of using the iterative solver without constraint is basically optimizing the memory. We can wrap up. Lisa, thank you for setting up the whole thing. Thank you, my colleagues from marketing, to set up this webinar. And thanks for the audience. Thanks for everybody to show up and take a nice hour from your time to attend this webinar. Please feel free to address your questions and your concerns directly to me, myself, or my colleagues, my emails. And thanks again, and have a wonderful day.